All right. Uh, Today's class we are basically going to talk about introduction in organic chemistry, topic 4 especially. I'll try to do it from the first. Okay, let's start. Okay, so what do we know about organic chemistry from the first? You start. Today's class is basically a revision class. Am I clear? So I'm assuming that you have an idea about the topics which I will discuss from before, at least some idea. Is my assumption okay, Mohideen? Okay. So today is just going to be a revision class, basically. So let's talk about the safety in chemistry experiments. There are three keywords which you need to remember for your exam, and they might also come that what is meant by you know risk and everything and all. Uh, so if I talk about 1 minute, okay, let's start. So hazard is basically in any action that has the potential to cause harm or damage. Risk is the probability of someone being harmed or something getting damaged when exposed to a hazard. So there is a difference between hazard and risk. Risk is basically a mathematical term, like it's basically a probability. So there is we tend to I think you've seen this in news is that there is 48% chance of the world going into a recession, the world's global economy going into a recession or something, right? So that probability which you get to see in the various news outlets or in internet, that probability is basically the risk, and this probability defines that how much chance you know or the how much potential there is for someone or something to get harmed or to get exposed to a dangerous situation. Am I clear? Did you understand? Hello. Okay. Now, then there is the risk assessment to identify the hazards in a procedure and to take measurements to reduce the risk. Now, obviously, risk is basically the antidote. A risk assessment is basically the antidote of a risk assessment, in my point of view. It basically means that if there is a risk, now what are the things I should or what are the measures I should take in order to reduce that risk. So the things which are done in order to do this, those things are known as risk assessment. Now what are the things that are done in risk assessment? You basically identify the hazards during a procedure. Here by procedure we get to mean is that any sort of experimental uh, any sort of experiments that you are doing, for example heat under reflux, or for instance you are mixing acid and base to produce some sort of a salt reaction, salt or something like that. So whatever the risks are associated or whatever the hazards which are associated with the procedure or the experiment that you are going through, at first you identify those hazards, okay, and then you take the measurements or the required measurements in order to reduce the risk. Say for instance, let's say you have two reactants, okay, you have two reactants. Let's say both of the reactants are very reactive. So if you react both of them together in a beaker, let's say, so there is a high chance that a vigorous reaction will take place, and the product coming out from the beaker, the product basically might get spilled out at very quickly. If we basically react both of these reactants together, considering if both of the reactants are very reactive, okay. So if a vigorous reaction takes place, the product producing may get spilled out, and this, let's say this product is corrosive, and we all know what's corrosive. Corrosive basically means that when it comes to the contact of your skin, it tends to cause harm to your skin. Okay, so now this is the hazard basically. Now what is the measurement in order to reduce this hazardous risk? Well, the measurement is pretty simple. We tend to add very slowly one of the reactant, okay, So let's say reactant A is there is already in the beaker. So instead of adding the reactant B all together, we tend to add it dropwise. In this way, the reaction won't progress vigorously, and the product won't be produced so quickly, therefore reducing the risk of it getting spilled out and causing you harm. So this is what risk assessment means. Am I clear? Did you understand? Okay. Okay, fine. So there are some examples, as you can very clearly see that many chemicals that we use in the lab pose hazards, but there are always ways to reduce the risk. This is one example, like strong acids have the potential hazard of causing skin burns. Most of the acids in the world are corrosive. Basically, they tend to degrade your skin somehow when it comes in contact. So to reduce the risk of getting harmed by using acids, we tend to use acids. Either we basically provide it in low concentrations, or not connotations, we tend to provide it in low concentrations, and we tend to wear gloves and goggles. Goggles is there in order to ensure so that when the acid basically so that your eyes can get protected if the acid gets spilled out from the beaker. And if I talk about gloves, the gloves ensure that the acid does not come in contact with your skin. Okay, so this is very important. So these are basically part of the risk assessment. The hazard is what? The hazard and the risk. The hazard is pretty simple. The hazard is that it can cause skin burns, and the risk is basically the probability of how much what is the probability that you might get skin burns if you do not take the you know required or the necessary required risk measurements basically. Okay, so did you understand from this example what is risk, hazard and risk assessment? Okay, so these are now in the main exam you will obviously most of the time they at least tell you to define the hazard, or other than that they provide you symbols. They either tell you to define hazard, or they provide you symbols, and these are the four most common symbols in our syllabus. So ensure that you basically remember this symbol. So uh, they might provide you this symbol and might tell you what hazard does this symbol represent. So this is the following hazard. For instance, in this case, this symbol basically represents that these test tubes basically contain corrosive liquids. So in most of the time we get to see that in chemistry the concentrated acids and alkalis are the most corrosive liquids. So yeah, you can take this as this is how this is what the symbol represents. And what is the antidote for it, or in other words, how can you what measurements you must take to minimize this risk? Well, since if you take if the acid and alkali is concentrated, so it kind of becomes corrosive. So instead of that, use dilute acids and alkalis, in my point of view. So in this case, dilute is basically the opposite of concentrated. Am I clear? So if the acid is alkali is less concentrated, so it become its corrosiveness decreases. And otherwise you can if it's not possible to use dilute acids and alkalis, you can simply just you can use concentrated solutions of acid and alkalis, but you should use in a smaller scale, or in other words you should use it in a smaller amount, not in large amount. So did you understand this part? Okay. Now, if I talk about this one, the exclamation mark or the skeleton one, or if I talk about the fire one, the flammable, the fire symbol basically represents that whatever alkene or alcohol or alkene, whatever the organic compound is, this symbol basically represents that organic liquid is highly flammable, meaning that when it comes in contact uh, with any sort of heat or oxygen, it may burn very easily. Okay, so that is why what is the antidote for it? You can simply just keep it away, keep the particular that particular organic compound or the liquid away from flames or sparks or any sort of heat source which might trigger the flame or make it flammable. Okay, and in the case of this skeleton symbol, this basically represents that the compound in the halogen, whatever it is toxic in nature, meaning that when it enters or when it comes in contact with your skin or your body somehow through, let's say, nose or your mouth, it might cause destruction to your health, meaning it might kill you or it might make you weak. Okay, so what is the best way? You can either basically wear masks in order to shield your nose and mouth, or else you can perform the whole, reaction which produces these toxic organic compounds and halogen within a fume cupboard. So in this way, the toxic halogen or the organic compound reactant being used or produced, it won't come in, it will be away from the atmosphere where you are standing, or where you are standing and performing the reaction. Okay, so these are two ways how you can basically keep yourself away from toxic organic compounds. And then there is another one, which is of course the exclamation sign. This basically represents that organic compounds, such as dilute acids and alkalis, are irritant, meaning that when they come in contact with your skin, they basically become red. What they're trying to mean is that they tend to basically instill a sharp pain in your skin when they come in contact. It becomes, the part where they come in contact with your skin, it becomes red due to excess amount of blood flowing through that part of your skin. So that is why these, when these liquids are irritant in nature, that time we basically use this symbol in order to represent them. And the best way in order to minimize this risk is that you should wash any spills of the skin immediately, meaning that, let's say mistakenly or somehow, that dilute acid or alkali came in contact with your skin, so immediately, without wasting any time, you get to wash off that spill of liquid, which might cause you irritant and make that part of and might make that part of your skin red immediately. So you should wash it with water. Okay, did you understand this one? Okay, okay, the oxidizing agent sign, I don't think that, do they have a oxidizing agent sign? Okay, okay, so the main difference in my point of view, there isn't of a much difference. In my point of view is that, okay, the main difference, I think it's pretty simple. uh, this is the oxidizing agent sign. Instead of the circular thing being present, the circular thing won't be present in the oxidizing agent sign. Uh, Something like this. Did you understand? This is the hazardous symbol of oxidizing agent. Which, look, oxidizing agents, it doesn't mean that they are flammable, but they might cause something to basically, they are itself not flammable, but they might basically cause other things to become, to get flammable. Did you understand what I'm trying to mean? Like why the sign is like this? Did you understand? Okay. So this is the difference basically what you're trying to, your question, the answer to your question is this one, that in the case of flammable liquids, you'll get to see a circle, and around the circle we'll see the flames. But in this case, only the flame is present when you try to represent the hazardous symbol of an oxidizing agent. Okay. Moving on, the next part. Now there are different types of formulae in our AS organic chemistry, and I think pretty sure you have seen this in IGCC level as well, which is what, the we have so many, like displayed, structural, general, skeletal, and obviously water hydrocarbons, the very old definition. It's basically compounds of carbon and hydrogen only, and that's basically it. In organic chemistry, most of the compounds we are going to deal are with hydrocarbons, and each hydrocarbons are arranged in different homologous series. They're basically, and the homologous series are basically distinguished by their functional groups, which is basically a group of atoms which are responsible for the specific reactions of an organic compound. Since functional groups determine the chemical properties of a specific organic compound, so in other words, they are also responsible for the specific reactions of that organic compound. Say for instance, for alkene, we have the following functional group. For alcohol we have OH, for carboxylic acid we have COOH, and then for alkane we have this. Okay, I guess you're familiar with functional groups. Moving on, if I talk about the other stuff, we have general, structural, displaced, skeletal formulae. The general formula is basically the empirical formula that applies to a series of compounds, and then the structural formula basically shows the hydrocarbon in addition to the functional group without showing all the bonds. This is an example of a structural formula where you can easily see that apart from the functional group, no other bonds are shown. But in the case of displayed formula, the opposite happens. Each and every bond is seen between each of the atoms in the compound. Okay, and the skeletal formula is basically the type of compound where basically the C and H, the CH are not shown, but the bonds are shown. Do I get to win? Do you understand what I'm trying to say? Like here, this here basically represents carbon, and with this carbon, one hydrogen is attached. That's what it try to represent. Did you understand? Okay. So that's structural formula, and that's the displayed formula. That's the skeletal formula for you. And general formula, there's another name for general formula. You can talk it as molecular formula as well. You can say that, or you can sorry, it's another name is empirical formula. Sorry about that. Empirical formula is basically the simpler version of molecular formula. What is molecular formula? Molecular formula, say for instance this one, two, there it molecular formula basically represents the total number of atoms, each type of atoms present in a compound. So in this case, carbon and hydrogen are the two types of atom, and we have three carbons, that's C3, and we have six hydrogen, so C3H6. That's the molecular formula for you. Now if they tell you to find the empirical formula is the simplest version of the molecular formula. So that would be, if you divide by 3 both sides, that would be CH2. Okay, so that's empirical formula for you. I basically divided both by 3, and that's what I got. I don't think you can simplify it anymore. That's the most simplest version, and that is the empirical formula. Did you understand? Okay, the next part is naming organic compounds. So see, homologous series, or basically is a family of compounds that have the following common properties. These are very important. They might ask you what is a homologous series, or what are the common properties present in a homologous series. Alkene, alcohol, carboxylic acid. These are various types of homologous series, and for each homologous series they have the same functional group, they have the same general formula. Say for instance, for alkane we basically know it's CnH2n plus 2. For alkene I believe it's CHN2n, right? And this is CnH2n, sorry, 2n plus 2O, right? I think you are familiar with all the general formula. Did you understand? Like for instance, n could be, here n is what? Here n is the number of carbon atoms or alkyl groups, carbon atoms or alkyl groups. So using the general formula you can find the molecular formula of each alkane within the homologous series. Say for instance, let's say for instance you want to find the molecular formula of pentane. Now we know pentane, basically 5 carbons are there, so N is going to be 5. So C5H2 times 5 plus 2. So that would be what? That would be C5H12. Did you understand? That's how you basically do the, get the alkane molecular formula using the general, the general formula. Okay. All right. Their consecutive members basically differ by an alkyl group or CH2. What they are trying to mean is that, say for instance, this one, if you draw this, so you have, so as you can clearly see, their consecutive chain, the consecutive chain or the consecutive members basically differ by a CH2 group. So you can see that the consecutive member, uh, basically they differ by a CH2 group. What I try to mean is that, say for instance, this is pentane, right? If I write butane, so what is happening here? If we exclude this carbon and this carbon right here, and if you compare it, how many CH2 groups are there? There are 3 CH2 groups, right? And there are 2 CH2 groups, right? And there are 3 CH2 groups. So both of them are basically in this, they are present in the same, both of these members are part of the same homologous series, which is alkane, and they basically differ by 1 CH2 alkyl group. Did you understand? That's what they're trying to mean basically. Okay, then they have the same chemical properties, considering then that they have the same functional group, and they are also have the same, common preparation methods, because since all of them have the same chemical and physical properties, so we can say that their preparation methods are going to be same. So this is how you basically, these are the prefixes which we use for, naming for each of the when, depending on the number of carbons being present. I don't think I need to explain it, separately. You can understand this. You can just check out this table. It's pretty simple. Okay, if I just use an example, say for instance, this particular organic compound right here. So if we start the naming from this side, 1, 2, 3, 4, 5, uh, and if we start it from there, so we have what? We have two methyl groups being connected with the second carbon. So what can we say? And another thing is that we have another methyl group being connected with the third carbon. So at first we identify the longest chain. So here the longest chain is obviously this one, right? This 5 carbon chain, right? That longest chain one is, the longest chain carbon chain. Its naming is going to, be placed at the end. And in the, there are two parts when you basically name an organic compound. In the second part, the longest chain the longest chain of the organic compound naming is done, and in the first part, the branched part naming is done. Okay, so in this case we have, why 2 2 is written, because in the in the second carbon, two methyl groups are attached, right? So that's 2, and in the third carbon we have the third, methyl group being attached. Now still all together there are 3 methyl groups, so obviously we are going to give tri, right? Because if it was, look, we basically use di, tri, or tetra. Di when there are 2, tri when there are 3, tetra when there are 4. Okay, so since there are 3 methyl groups, so we are going to use trimethyl. And in the second part, since the longest chain is a pentane, considering there are 5 carbons, so second part is going to be pentane. So altogether we can say the naming of this compound is 2,2,3 trimethyl pentane. Did you understand? Okay, next part, there are, you know a large number of organic reactions which we need to remember in our, or organic chemistry basically. So there is the, the following list of organic terms. Okay, we will, later on we will, clarify it in details, but if I talk about this, we have the addition reaction, then we got the substitution reaction, then we have the oxidation, and then we have the reduction reaction. Addition is basically pretty simple: when two molecules combine together and no other molecules are, substituted, and when two molecules combine together, they basically form the large molecule. And if I talk about substitution, it's a reaction It's the opposite of addition basically, where one atom or group is replaced by another atom. Say for instance AB, this is an example of addition reaction. But if I talk about AB, let's say let's say A plus B, so let's say something different happens. Say for instance uh, AC, let's say AC plus, let's say something else. Say for instance AB plus C is equal to AC plus B. So what happened is pretty simple. The reactant C displaced B and took its place. Okay, this is an example of a substitution reaction. Okay, an oxidation reduction, I don't think I need to say this. It's pretty simple. When a substance gains oxygen or loses hydrogen in a reaction, that's oxidation, and vice versa for reduction. Electrophile is a species that is attracted to a region of high electron density, such as a double bond. We all know that in a double bond, now this double bond may be present in many types of homologous series. Say for instance, it is present in the alkene homologous series, it is present in the aldehyde series, it is also present in the what, ketone series, right? And it is also present in the carboxylic acid series as well, right? So the fun fact is that all of these double bonds, they have electrons in them. So due to the electrons being, due to the shared pair of electrons being present in the double bond, they have high electron density. Okay, so which makes them partially negatively charged. So since they are partially negatively charged, they are able to attract their opposites, which is a positive species. So that means electrophile itself is positive. It's a positive species. Did you understand? That means it is positively charged. Did you understand? Okay. So then we have heterolytic and homolytic fusion. Now what is heterolytic fusion? It is the breaking of a covalent bond where both bonding electrons are taken by one of the atoms, and homolytic fusion is the opposite. So say for instance, if I talk about say for instance Cl. Okay, so sometimes what happens that halogens undergo homolytic fission. So what happens in the homolytic fission is, since both of these atoms, chlorine is obviously a diatomic molecule, so each uh, so each molecule basically contains two atoms of chlorine. So since both of them are identical types of elements, so they both have the same electronegativity, meaning that they do not have any electronegativity difference. So is it a polar or a non-polar bond? Tell me. Is it a polar or a non-polar bond? Okay, it's a non-polar bond, exactly. So what happens is that when this bond breaks down, the shared pair of electrons is equally distributed to both of the atoms. And the way and the process in which, during breaking this happens, this process is known as homolytic fission. Okay, fission basically means what, breaking down. And what homolytic means, why homo, because here both of the atoms are receiving equal number of shared pair of electrons and getting broken down to produce what, well, to produce radicals. Well, since both of them now contain you know uh, unpaired electrons, both of them contain unpaired electrons, now they are negatively charged, and this species is known as radicals. So what are radicals? We can say radicals are species which consist of unpaired electrons. So meaning they're itself negatively charged. Did you understand? That is what homolytic fission means. And what is the opposite of heterolytic fission? The breaking of a covalent bond where both bonding electrons are taken by one of that. Say for instance HCl. Now this is a this is a polar bond, right? Because there is an electronegativity difference considering both of them are of different elements. So in this case, the higher electronegative element is going to take the shared pair of bonded electrons when this breaks down. So in the process in which it takes, in this case chlorine obviously has higher electronegativity, so chlorine is going to take both of the bonding electrons. So as a result, the process in which this breaks down, this is known as heterolytic fission. In this case, what happens is that one radical is being produced. Am I clear? Did you understand? And obviously we have plus H plus being produced. So this is what it is. Did you understand? Okay. Now we have polymerization. It is basically a reaction where a large number of small molecules, the small molecules are known as monomers, they react together to form one large molecule, and that is basically known as polymer. Okay. Uh, Please wait for 1 minute. Okay. Moving on, if we move on to the next part, the isomer section, right? What are structural isomers? See, saturated hydrocarbons. Now, there are three things before you understand what are structural isomers. There are some definitions which you need to understand. The first one is saturated hydrocarbons. Obviously, there are two types of hydrocarbons: saturated and unsaturated. What are saturated? Molecules with single bonds only consisting of carbon atoms. One example is obviously alkane. So, what will be unsaturated hydrocarbon example? Alkene, considering they have at least one carbon to carbon double bond in their structure. Okay, so that is what that is the difference between saturated and unsaturated hydrocarbon. Now, cycloalkanes is another form of saturated hydrocarbons, but in this case what happens is that the alkanes are found in a ring structure consisting of three or more carbon atoms with the general formula CnH2. Now, the fun fact is that even though it's an alkene, the alkene is basically in a ring form, but the general formula changes to the alkenes one. Did you understand what I'm trying to say? CnH2n is basically alkene's general formula. I think you have understood that. Hello. Okay. So that is what happens. Now, if I talk about the chain isomers, what happens is that this is basically when the carbon backbone is rearranged by adding the side chains. So, if I give you some examples, for instance, butane, pentane, hexane, heptane. So, if I talk about butane, how many number of possible chain isomers might there be? Say, for instance, you got two. Say for instance, how many? They say two, right? So let's say, can you tell me two, the name of the two? Will you try with me? What is the name of this one? Do you know, or do you have issue? Yeah, continue. This is 2-methyl, 2-methyl propane, exactly. Okay, and there is another one which is cycloalkane. So basically you can just write it down as what? Like this. Am I clear? So how many possible chain isomers are there? There are two possible chains. So this is what? Cyclobutane. So these are the two possible chain isomers. So like this, you can find for pentane, you can find for hexane, you can find for heptane. So these are the corresponding possible chain isomers present for each of them. Okay, fine. And this is what it is. So this is the 3D representation. Now we have some other things as well: positional and functional group isomers. Now, isomers which are based on functional groups that are at different positions. Remember one thing: isomers which have functional groups at different positions, and functional group isomers are basically isomers which have different functional groups. Do you understand the difference? Okay, so the next part is pretty simple. uh, Positional isomers have the same carbon backbone, but their functional groups are at different position. So the next part is pretty simple. Now the main point here is that another difference is that, look, if the position of the functional group changes, what happens that their physical properties such as boiling temperature is also changed. So for instance, butane 1 and butane 12. So if the OH basically gets shifted to the second carbon, its boiling point decreases. And in this case, for instance, if the function both of them have completely different functional groups, you can see in this case there is an alkene functional group and here there is an alkene functional group. So obviously they are going to have different physical and chemical properties because their functional groups are different. Okay, with this I believe a lot of part is done. We are moving to the crude oil section. 1 minute. Okay, now let's start with the fractional distillation of crude oil. Okay, so now what is the fractional distillation of crude oil? I think we studied this back in IGCC level, that what crude oil is a mixture of hydrocarbons which is largely made up of alkanes. Okay, right? And it's basically the main energy source of the whole world. 80% of the world basically runs with crude oil. Without crude oil, a lot of essential energy products cannot be produced. Energy products, as in products associated with petroleum, or car fuel, jet fuel, whatever that is. This crude oil, which is basically a chain of large hydrocarbons, this crude oil is basically divided into several fractions and then used for different applications. All right, so what happens, petroleum, in other words crude oil, is passed through the heater so that it vaporizes, and and then passes into a fractionating column which has 400 degrees Celsius to 3 or 350 degrees Celsius temperature below, while here it is only 40 to 35 degrees Celsius above. So what happens if you check out the second point is that fractions with very long chains do not vaporize but remain in the bottom of the column as a residue. So, sorry, you can't? Oh, wait. Sure. I don't, I believe it's being shared. Do you see it? Now do you see it? Hello? Okay, so check this out. So in the fractional distillation, what happens is that we basically tend to, you know, uh, separate crude oil, right? And this is the fractionating column, and there you have the crude oil, and which is basically vaporized and then sent. There it is being sent through the heater and then vaporized, and the vaporized form is passed through the fractionating column. And in this fractionating column, there is a temperature gradient where below the temperature is within 400 to 350, and above it's 40 to 35 degrees Celsius, something like that. Now, the main thing is that since the crude oil is a large chain of alkanes, the fractions which basically have longer chains, they do not vaporize, but they remain in the bottom of the column as a residue. What they're trying to say is that the longer chain hydrocarbons present in the crude oil, they tend to vaporize or vaporize into, fractions at the bottom part of the fractionating column. Say, for instance, bitumen has the highest boiling point, and that is the reason it's why it does not vaporize and just stays as the residue. Now, as the other fractions, as they basically as the crude oil gas basically rises up, they tend to distill at each at according to their respective boiling points. Remember one thing: the lower the boiling point of each chain, each hydrocarbon chains, the higher up the fraction distills, meaning that the refinery gases have the lowest hydrocarbon chain length, and that is the reason why they basically distill at the topmost part of the fractionating column. And these are the ones, basically they distill according to their boiling point. So the lower boiling point ones basically distills at the top, while the higher point ones distill at the bottom. Did you understand? Petrol, naphtha, kerosene. I think you know what's diesel oil, which is basically used as fuel oil in lorries and trucks. Fuel oil is basically used for powering up ships, while lubricating oil is an essential one used for powering motorcycles and everything. Petrol is another one for cars. Did you understand? Bitumen is the one which is used for producing roads. Bitumen or asphalt roads are very much, it is basically mixed with asphalt, and concrete roads are produced. I believe you have seen them when engineers bring a large chunk of black thing. That black thing is which tends to look like coal, that is basically bitumen. Okay, so these are some of the common properties of the topmost fractions. As you can very clearly see, that they are smaller molecules, they have lower molecular mass, they have less number of carbons, lower boiling point, they're less viscous, more volatile, lighter color, and they have more efficient combustion. In the case of bottom fractions, they are larger molecules, they have higher molecular mass, they have more number of carbons, they have high boiling point, they're more viscous, they're less volatile, they're darker in color, and they're kind of less efficient in combustion. Okay, moving on, the next part, we have cracking of alkenes. Okay, first of all, there is a big good thing is that the breaking, what is cracking? It's the breaking of the carbon to carbon bond in of long alkanes into shorter alkanes and alkenes. The main thing is that the shorter chain alkanes are much more in need because they're more in demand compared to the longer chain ones. Now obviously the shorter chain alkanes are very less in amount. So how, what is the only way? Well, we can break down the longer chain ones and produce the shorter chain alkanes which are in huge demand. So there is this process which is known as thermal cracking, which occurs at 1000 degrees Celsius and 70 atm pressure, that tends to break down the cc bond of a long chain alkane, and as a result one shorter chain alkane and an mandatory alkene is produced. Okay, you understand? The shorter chain alkene basically could be, let's say, refinery gas, which is basically used as a cooking gas. I think you've heard about LPG, liquefied petroleum gas. Have you heard about it? Hello, have you heard about liquefied petroleum gas? Yeah, exactly. So refinery gases are present in LPG, which is basically used for cooking. The next part is the reforming of alkanes. Remember one thing, that not all short alkanes are made by cracking. Some of them are useful for the engine of vehicles, we know that, right? So straight chain alkanes combust less smoothly and efficiently in the engine than branched or cyclic alkanes. This is an important fact, that always remember that compared to straight chain alkane, compared to straight chain alkanes, the cyclic or the branched one, say for instance this is a cycloalkane, we can clearly see that they tend to combust less smoothly. We know in that inside the engine the combustion of alkenes takes place, which results to the production of heat energy that basically powers up the whole car and allows it to move forward, isn't it? So it's very essential that we use a type of fuel which has enough efficient alkanes for being combusted, so that they can be so that enough heat energy is released for powering up the car. This is very important in the case of economics, in the case of engineering economics is very important, so remember this. And there is another thing, that they have cyclic alkenes tend to have a high octane rating, which allows the fuel to burn smoothly in the car engine. Remember, octane rating is a way of showing that it's basically a measurement factor of alkenes, which basically allows us to judge which fuel is basically more efficient in during combustion. And the fuel which is more efficient during combustion, that tends to release the most amount of heat energy, which is our desired thing, isn't it? Because if more heat energy is released, the more higher way the car engine can be powered, and the car can move at a higher speed more efficiently, right? So this is very important. So the octane rating is a way of measuring that efficientness. What is reforming? It's the conversion of the straight chain alkenes into branched on or cyclic alkenes. This is a reforming reaction. Well, basically where in the presence of a platinum catalyst, you can convert a straight chain alkane into a reformed branched cyclohexane, along with one hydrogen gas is produced, considering one hydrogen gets comes out from the you know basically comes out from the alkane. Okay, did you understand? Okay, now let's move on to the electrophilic addition of alkenes. Now this is very important, as so far we understood what is alkenes, right? We know that its general formula is CnH2n, right? It has the same functional group of carbon to carbon double bond, right? We know what is an alkene, isn't it? And it is what, unsaturated or saturated? It is an, exactly, it is an unsaturated hydrocarbon, considering they have at least one carbon to carbon double bond. Examples include so many. You have butane, you have butene, you have 3-methyl propene, and so on and so forth. Now, what is the mechanism in which alkenes undergo addition reactions? Well, the mechanism in which alkenes undergo addition reactions is electrophilic addition. So what happens is pretty simple, and remember one thing, that electrophilic additions have a 100% atomic economy. What is atomic economy? You know this? It is what? It is the molecular mass of desired product divided by molecular mass of total products times 100, right? This is what it is. It is basically the atom economy of an electrophilic addition reaction, and fun fact is that this ratio is 1. The reason why it is 100%. Okay, now it is the double bond in an alkene which makes them so reactive. Remember, little while ago I told you that the double bond is electron rich area, meaning that it contains bonded pair of electrons, so it has a high electron density, right? So as a result, it can be easily attacked by positively charged electrophiles. Am I clear? Positively, hello, positively charged electrophile, isn't it? Say for instance, this is an example of an electrophile. So look, what happens is that this here basically, look, this is an example of an electrophile. Okay, now remember that electrophile consists of two atoms, all right? One is obviously partially positively charged and one is obviously partially negatively charged. So the partially positively charged is basically, the partially positively charged part of the electrophile tends to attack the high electron density rich of the carbon to carbon double bond in the alkene when the electrophile comes close to this, to this region. Okay, so when it comes, what happens? When it gets, when it attacks this, so what happens is that automatically via heterolytic fission, this bond, the electrophile bond, breaks down. So in heterolytic fission, what happens? We all know that what happens, the higher electronegative atom basically tends to take the bonded electrons, isn't it? So the process in which it is breaking down, it is what? Heterolytic fission, right? Did you understand? Okay, so this is what happens later on. The what After, this basically causes one of the bond to break down. After the electrophile attacks, one of the bond basically breaks down, and this allows one of the, the partially positively charged, part of the electrophile, which has gotten broken down from the acyclic fission, that joins with one of the carbon. Now obviously another carbon produces a carbocation. Considering, now carbocation is what? Obviously it's positively charged, right? And we can clearly see what is it? Is it a secondary or a primary carbocation? We can clearly see this carbon is attached to two carbons. So is it secondary or tertiary? It's a secondary carbocation, right? Did you understand? This is very important. Secondary carbocation. So the partially negatively charged part of the electrophile, which basically which got broken down via heterolytic fission, that gets attracted towards the positively charged carbocation, and it attacks and eventually joins and produces this additive product. Okay, so that is how addition reaction of alkenes takes place. If I give an example here, check this out. So we have the alkene propene, and then we have this electrophile right here, HX. This is a hydrogen halide. Now obviously the halogen is more electronegative than the hydrogen down here, right? So what happens? Pretty simple. The higher electronegative element basically, takes all the bonded pair of electrons via heterolytic fission, right? When this whole thing comes close to the carbon to carbon double bond, and attacks the higher electron density, what, higher electron density double bond. Okay, so when it attacks, what happens, the positively charged part of the electrophile, in this case the hydrogen atom, it donates a pair of electrons. Okay, since this is electron density, since this is electron rich, it when it attacks, it donates a pair of electrons to this partially positively charged hydrogen atom, and allows it to form a bond. As you can clearly see, a bond is formed. Did you see this? This is where the hydrogen attached. Now obviously, since the double bond got broken down via this process, one of the carbon produces a carbocation, a secondary carbocation to be exact. Okay, now there are two ways basically. You might answer this, sir. The carbocation could be produced in the second carbon, or it could be produced in the second carbon, or it could be produced in the first carbon, right? So there are two possibilities. That is the reason there are two possibilities, or there are two ways in which this reaction proceeds. Now obviously the only difference is that two products will be produced. The only difference is that one will be major and one will be minor. Now how will you understand which one is major and minor? By checking the carbocation. We know what, we know that a third degree carbocation is more stable than the second degree, and obviously the first degree is more less stable than the second degree. This is the trend, isn't it? Always remember, the halogenoalkene consisting of the higher degree carbocation, that is more stable, and the more stable one will produce the major product. Did you understand? So in this case, the secondary carbocation is more stable than the primary carbocation right here. So whenever the negative part will attack these two carbocations, the carbocation attacking the secondary carbocation will produce the major product, while the latter will produce the minor product. Okay, so since this is connected with the second carbon, this is called secondary halogen-alkene, and since this is connected with the first one, it's known as primary halogen-alkene. So did you understand why this whole mechanism or this reaction proceeds in two way? Okay, this is how it works. Now what happens when you react an halogen? Because now we know in this case, it's the same case basically. Okay, in the halogen, what happens is that the same process takes place, because in halogen we know that both of the elements are positively, both of them are of the same type. So this is what happens: one of them becomes partially positively charged, another becomes negatively charged, and the same thing basically happens. The attacking, remember the arrow sign, the direction of the arrow sign is very important. In the main exam, you will be told to provide the arrow signs, or they might provide you the arrow sign in the opposite way, and they might tell you to correct it, or might tell you what is the mistake done here. Do you understand? This type of questions may come. Did you understand? And whatever I explained, these are provided, these are written in professional words down here. You can clearly see it down. Shall I move on to the next part? Oh, by the way, I forgot to mention, this whole thing is known as an intermediate. This is also known as an intermediate. And remember one thing, they take place under room temperature. Okay, isomers, geometric isomers is very important. Uh, Now, geometric isomerism is kind of shown by carbon to carbon double bond, basically. So, if I talk about, there are two types of geometric isomerism. You have EZ Z isomerism, or cis trans isomerism. So, it is only possible in saturated compounds. The atoms or the functional groups attached to the, you know, alpha bonded carbon atoms are not fixed in their position due to the free rotation about the carbon to carbon double bond. Okay, now this is very important. In unsaturated compounds, you have the carbon to carbon double bond. Now according to unit 1 concept, I think you know what, you know that double bond is basically produced due to end-on overlap of d orbitals, sorry, p orbitals, isn't it? It is produced due to what, sideways overlap of p orbitals, right? That is how a double bond is produced. But in the case of a, and we know in a double bond, this is an example of a pi bond, and there is what, a sigma bond, right? So the combination of this sigma and pi bond produces the carbon to carbon double bond, isn't it? And on the other hand, in case of a sigma bond, only what, the end on overlap, or what, the end on overlap of a d orbital and spherical s orbital, whatever it that is, whatever the combination is, due to these overlapping, the sigma bond is produced. We know that, right? Now, the main fact here is that due to the sideways overlap of the p orbitals, they cannot rotate about their axis. This is an axis, okay? Now they cannot rotate, meaning whatever the atom is present here, these electrons cannot come down, while the electrons present here cannot go there due to the restricted rotation. But in the case of sigma bond, it can be done. Okay, did you understand what I'm trying to say? So in the case of carbon to carbon single bond, the rotation is possible, but in the case of double bond, there is no rotation. There is restricted rotation. Did you understand? Now this is very important. So due to this restricted rotation, you know, alkenes tend to show geometric isomerism, and there are two types. We have cis or trans isomerism, and then you have what you have what ez isomerism. Now look, this is very important. If I give cis isomers, you have to understand what is cis isomers. Cis isomers have two functional groups on the same side of the double bond or the carbon ring, both above the carbon to carbon double bond or both below the carbon to carbon double bond. Say for instance this one down here. So if I talk about, you have what, uh, you have two things, right? So this is an example of a cis and trans. Now this this is I think I talked about a little while ago why saturated compounds called have unrestricted rotation. So they just provided you a diagram way of representation. You can see the rotation about the carbon to carbon double bond single bond is possible. So the two molecules can change from one conformation to the other. The two molecules are identical, right? Say for instance these may go up while these may go down. Do you understand what I'm trying to say? I'm trying to say is that since these have pi bonds, sorry, this is they have sigma bonds, they have unrestricted rotation, meaning these OH groups can go up while these H groups can go down. Did you understand? Or the other way around can happen. They, what's it called? They might change their places. Like this H can come to this H place, and this H can go to that H place. This H can go to this one, and this one can go to this one's place. And I think you understand what do they mean by these arrow signs. These black strip signs represent their outs, they're coming out of the page. Am I clear? And what does these striped ones represent? They are into the page. This is what, out of the page. Did you understand what I'm trying to say? Basically they're trying to say they come out of the page, or they're like this. And the strip signs represent they're in the back side of, this is a 3D diagram. The no, I think you know this, the black stripes and the striped one and the black ones basically represent the 3D version. Since it's a 2D diagram, the 3D diagram is basically represented via this format. Did you understand? Okay, so this is what happens. Now in case of alkenes, or when where there is a presence of pi bond, there is unrestricted rotation, meaning these OH cannot go there, and H cannot, this OH cannot go there, and H cannot come here. H H cannot go in the place of this OH. So basically due to unrestricted rotation this cannot happen. So there is no interconversion. Now what is, how do you determine the, how do you identify these isomers? Now what did we say about cis? Both of the functional groups, for in case OH, if both of them are, both of the identical functional groups are in the same site, as you can see this is known as cis isomer. Cis, and obviously we know the compound's name is 1,2-ethene diol, so obviously it's cis 1,2-ethene diol. But in this case you can see this, the identical OH groups are not present in the same side of the carbon to carbon double bond. So in this case they are present diagonally. One is present in this side, another is that side, and in the H is present this side, it is another, it is present this side. This format is known as trans isomer, or in this case trans 1,2-ethene diol. Did you understand? Okay, and as you can see clearly, no rotation around the carbon to carbon double bond is possible, so the two molecules cannot change from one conformation into the other. Each isomer has a different chemical and physical property, so meaning that cis has, and cis and trans, since both of the functional groups position are different, both of them will have different chemical and physical properties. A little while ago I think we discussed about functional isomerism, right? We talked about functional isomerism, isn't it? Where an important fact is that since the functional groups are different, they have what? Different physical and chemical properties. Did you understand what I'm trying to say? Same for like this. Okay. Now, deducing E Z isomerism. Now, what is E or Z isomerism? Now, it's this kind of opposite of cis or trans isomerism, right? Okay. The main thing for cis or trans isomerism exists that we need two different atoms or group of atoms on either side of the carbon to carbon double bond, isn't it? Say for instance, we have two different types of what? Carbon to carbon, we have two different types of, atoms being, or what's it called, groups, atom groups being attached to the carbon to carbon double bond, isn't it? But this means what? This means that 2 methyl propene cannot have, uh, for example, this one here. Why do you think this one does not have cis or trans isomerism? Why? Because you can clearly see what? That both of them are, like, you can clearly see, like for cis or trans isomerism to happen, what is important? That each of the carbon must, they should not contain two identical groups attached to each other. Like, one carbon should not have two OH groups attached, because if this happens, then cis or trans isomerism won't exist. What? For cis or trans isomerism to exist, each of the carbon should have two different types of hydrogen, atoms being attached with it. Am I clear? So in this case, we can clearly see this carbon has two identical types of atoms being attached. In this case, two methyl groups are attached. So obviously, cis or trans isomerism is not possible for this. So how can we reduce this isomerism? Check this out. We will use the, you know, uh, but there is one way you can do it. If we do one thing, that if we just take this CH3 there, and if we take H there, then it is possible to distinguish the isomer via cis and trans format. Now, how do you do this? It's pretty simple. There is one way you can do. There is one way you can do EZ isomerism, which is, for instance, this one. Check this out. This one, this one, this one, this one. You can clearly see what? You can clearly see that there are four different types of, atoms being attached with the carbon to carbon double bond, isn't it? So this, in this case, what we do is that we will use the EZ isomerism. Am I clear? So remember one thing. What do you understand from cis trans? For cis trans to happen, the carbon should not have two identical carbon, atoms attached to it. Okay. And for cis trans to happen, another thing that is important, that two different types of atom, atomic groups must be present. In this case, what are the two different types of atomic groups? We have CH3 and H, right? This is one condition very important for cis trans to happen. And another condition is that one carbon atom must not contain, identical, atom types. Am I clear? So these are the two conditions required for cis trans isomers to happen. Now, when will we apply EZ isomerism? When you will see four different types of four different types of atomic groups attached to the carbon to carbon double bond, only then you will use EZ isomerism. Did you understand? So how will we use it? Check this out. So these R1, R2, R3, R4 are used to represent four different types of, uh, you know, uh, atomic groups attached to carbon double bond. So this is basically used an example down here. You can clearly see R1, R3, R2, R4. At first, you need to apply the CIP rule in order to, solve it. So if we use the CIP rule, let us check out R1 and R3. Okay. So who has the higher molecular mass here, bromine or hydrogen? You tell me. Bromine has the higher molecular mass. In case of R3 and R4, who has the higher molecular mass? Oxygen, right? OH, isn't it? So in this case, R2 has the higher R4. And in this case, what? R3 is higher than R1. So how will we basically prioritize the groups? Well, we'll prioritize by according to their molecular masses. So in this case, bromine is the higher priority group in this for this carbon, and for this carbon, what this is the higher priority group. R3 and R2 are the higher priority groups. Now, what does E mean? E basically means antigen, meaning opposite. All right, very important. And if I talk about Z, what does Z mean? Z basically means Zusammen. Both of them are German ones, but both of them have different meanings. And Gigen basically means opposite. Zusammen basically means together. So what happens is pretty simple. If the higher priority groups are present in different sides of the carbon to carbon double bond plane, this which one represents opposite? E, right? So this is an E isomer. And if the higher priority groups are present on the same side in the carbon to carbon double bond plane, so what does Zusammen reference together? So this is an example of a Z isomer. So did you understand how do you identify E and Z isomer? Okay, so this is very important. So this is an example I showed you in compound A and compound. So this is E and this is A. So the name of the compound is 1 bromo 1 propane 2 ol. So this will be E 1 bromo 1 propane 2 ol, and this will be Z 1 bromo 1 propane 2 ol. Okay. So with this, I think we have covered 90% of it. I'll take another class maybe on Tuesday. Okay. With this, that's it for today. Basically, bye bye. And